Hey, this is Horner, and this is 1998, question M1. We have a couple gliders on an air track, and this one has a spring on it, the other one does not. This one's obviously heavier than the other one is, and they're going to collide. When they collide, there is some photography going on, and there is a strobe that is recording the positions of the glider A at 0.1 second intervals for a total time of 2 seconds. During which it does collide with glider B. So the diagram down here represents the motion of glider A. The positions of glider A at the end of each 0.1 second interval are indicated by the symbol A against the metric ruler. The time elapsed T after each 0.5 second is also indicated. So it's really not an A, it's just kind of a little mark that comes across here. They want us to find the average speed of the glider A for each of the following time intervals. So we're going to do it from 0.1 to 0.3 seconds first. So I'm going to scoot this down a little bit so we can see. And we just need to find this velocity. So to do that, we know velocity is just equal to change in position over change in time. So for this first one, this is going to be 0.3 meters minus 0.1 meters. And we're going to divide that by 0.3 seconds minus 0.1 second. And you can kind of see this one's going to be 1 meter per second. So that is from 0.1 to 0.3 seconds. For the 0.9 to 1.1 seconds, so this is 0.5, 6, 7, 8, 9. So there's this one. And then we've got 1.1 seconds. So this is 1.0, here's 1.1. So we've got a smaller space here. We're going to say same thing, V is equal to delta X over delta T. It's important to write the equations. We're going to take 0.99, so that's that position here, minus 0.87, and divide that by 1.1 seconds minus 0.9 seconds, and we end up with 0.6 meters per second. For the very last one, this one is from 1.7 to 1.9 seconds, so we're going to do 1.7, so here's 1.567, and then 1.9 seconds, which is going to be, we want to go from 1.9 to 1.7, so you have to be careful. See, I did this already. That's position. Time is down here, 5, 6, 7, 1.7 to 1.9. So that is the interval that we want. So let's go ahead and do it. I'm actually going to do it here instead of down below because it's a little bit easier to see actually what we can do. Yeah, there we go. So our velocity here is delta x over delta t. That is equal to 1.18 meters minus 1.14 meters divided by our change in time, which is 1.9 minus 1.7 seconds, and we get 0.2 meters per second. So you'll see that this thing is decreasing in speed. Next thing that they want us to do is draw a little graph here. It says, so on the axis below, sketch a graph consistent with the data above of the speed of the glider as a function of time for that 2-second interval. So we'll make it a little bit bigger, make it a little bit easier to see. For our very first time, we know that it was originally traveling at that 1 meter per second. So we're going to start right here. And then at about 0.7 seconds is when we start to decelerate. So we're here, and we know that we're going to go all the way down over here at about 1.3 seconds. We know that our speed has come down to about right here. So that's our new velocity, then it tails off. So here's our first section. And then what you have to be careful of is you need to have a curve. And that curve will move through, but we have to figure out that at 0.6 seconds, we've got to go through this point. And then it keeps moving through. And then there is an upward facing curve at this point. And then we just go straight across. So From here down, you'll see the downward facing curve. We've got a straight line, then we've got an upward facing curve. So this, if you drew a smiley face, that would be a frowny face right here, and then you have a smiley face here, okay, which will help you kind of with your accelerations. And that would be 3 points. Next thing they want us to do is use the data to calculate the speed of glider B. And so we're going to do that. The speed of glider B immediately after it separates from the spring. So you can either do this using conservation of momentum or conservation of energy. Either way is appropriate. So here we've got the mass of A times the velocity of A original plus, so we'll just put an I there, the mass of B times the velocity of B initial. And we know that this is 0 because it's not moving yet. And that's equal to the mass of A times the final velocity of A plus the mass of B times the final velocity of B. So we've got everything we need. We know that this is 0. We've got 0.9 times 1 meter per second is equal to 0.9 times 0.2 meters per second plus, and then 0.6 kilograms for B times B's final speed. From this, we can just solve for VB, and you'll end up with 1.2 meters per second. All right, so at this point, they want us to sketch the velocity of B over a period of time. And so we know that it is 0 until this 0.7 seconds, at which we start to have a curve. We know that at somewhere in this area, so we know that at 1.3 seconds, we should have a speed of 1.2. So we're going to put that right here. And we know that somewhere in between, we should have at 0.6 and 1.1, we should have a dot there. So here we're going to come across. We're now going to have an upward facing curve. It's going to go straight, whoops, it's going to go straight through here and then be a downward facing curve. And that doesn't look real good, so let's go back. Oops, I need the eraser. And let's, oh, yeah, that was real fun, wasn't it? Okay, so now we can erase these. We'll make them look a little bit better here. So we've got our point, got a pen again. We've got our point here at the 0.6, and then we have another point up here at 1.3 and at 1.2. And now we're going to make a smoother curve there. This is going to keep going straight up, and then it's going to curve again, and then we're going to come through. So now we're set. So now we've got all our points. So that's area 1. We could call this area 2, and then we could call this area 3. And you get a point for each one of those. You just have to make sure that you have the right things here. So now at this point, the next thing that you have to do on the problem for letter D is they say, is the collision elastic? Justify your answer. So here's your graph of kinetic energy. Notice that you don't lose any kinetic energy, okay? So it goes down, but it then comes right back up. So yes, it is elastic. So E-L-A-S-T-I-C. I would just put yes and then an arrow and say yes, it is elastic. And we know that the change in kinetic energy is conserved, okay, in a perfectly elastic collision. So that's why it's got to be perfectly elastic. Next thing they want us to do is we just have to explain why there is a minimum kinetic energy curve at 1 second. And this is where the spring is fully compressed. So the spring is fully compressed and is storing S-T-O-R-I-N-G, sorry, maximum potential energy. And we know that our kinetic energy max should be equal to our potential energy of the spring max at different times. So when the spring is completely compressed, there's no kinetic energy, it's all potential in the spring. But then when there is no potential energy of the spring, then there is just total kinetic energy of the spring, and that is at maximum. And we know that that is happening at 1.00 seconds. And that is the end of this problem.